let's keep looking at limits. Specifically, I want to talk about left-handed and right-handed limits. And we'll also get to the definition of what a limit really is. Let's think about this function f of x being 1 over x. And fill in a table. If x is 1, then the reciprocal of 1 is just 1. The reciprocal of 1/10 is 10. The reciprocal of 1/100th is 100. We got 1,000 and 10,000. And when we're trying to figure out what the limit is, we're thinking about as x approaches 0. So that's what's happening on the top line, is that those x values are getting smaller and smaller and smaller and getting closer and closer to 0. So what happens to the y values, that f of x value? We see that that value is getting larger and larger and larger. So it kind of looks like that the limit as x approaches 0 of f of x is going to be infinity. And we can visualize that. I mean, we see the pattern that's happening, that if I get, if I may put another 0 in that decimal, then it's going to put another 0 at the end of the thousands. So yeah, it makes sense that the limit should be infinity. But what happens when we still approach 0, but we approach it from the other side, from the negative side? So starting at -1 and letting it get closer to 0. We see that what happens to our y values, our functional values, is they are also getting larger and larger, but they're getting larger and larger in the negative direction. So that will be another infinity, but that limit's going to be negative. And we run into a little problem here, is that, well, what is the limit then? Is it going to be that in positive infinity, or is it going to be that negative infinity? Notationally, what we're dealing with is what we call left-handed and right-handed limits. See, we're trying to get to the x value of 0. And we saw that if we started on the positive side and got closer and closer to 0, our graph was going to grow to infinity. And that's what we found first. How we actually should note it is with this little plus sign as a power after the number. This is what we call the right-handed limit, because we're coming from the positive infinity side. And if we were to start from the negative side, that's where we saw that the curve was going down forever and ever, and that gave us a limit of negative infinity. When we come at it from the left-handed side, that exponent, so to speak, after the number, it would just be the negative sign, saying that we're coming from the left-handed side. Overall, our limit is an expectation, all right? That, remember, when we're talking about a limit, we're not actually getting there. We're letting x get closer and closer and closer to 0, and that limit is our expectation of what we think is going to happen. And when we have this conflict coming from the left and right, approaching different values, we have these different expectations depending on which side we come from, then we can't be definitive about the limit, and we say that it does not exist. So as a formal definition, I mean, we've been running kind of on intuition so far, but the actual definition of the limit is that the limit as x approaches some constant c of f of x to equal L, some other value. The only way that can happen is if and only if we approach it from the left and we get that L, and we approach it from the right and get that same value. Only if our expectation from the left and the right are the same can we say that overall our limit is that value. So let's say g is this piecewise defined function where it's the square root of x plus 1 if x is greater than or equal to 3, and it's going to be x squared if x is less than 3. And the first thing we should probably do is graph it. So thinking about the first piece, the square root piece, that's going to have a vertex at -1. And it'll be like it's the top half of a sideways parabola. So it's going to look like this. Okay? But we want it only to look like that from x equals 3 right here. And of course, the y value at that point, we plug 3 in. 3 plus 1 is 4. Square root of 4 is 2. Right? So we want to keep the part of this graph that is only when x is greater than 3. So I'm going to go back and erase the part that's less than 3. I don't want that. Now, for the second part of our graph, x squared. That is a vertex at the origin. See, we got 1. 2 squared is 4. 3 squared is 9. So we're looking at a parabola that looks like this. And of course, we don't want the entire parabola. We only want this part up until x is 3. So I'm going to erase the rest of it. The value at this point, when we plug 3 in, 3 squared is going to be 9. Now, what's the limit? Well, if we look at the limit as x approaches 3 from the right of g of x, that's when we're going to be on this portion of the curve. We're going to come at 3 from the right side. And we expect that our value would be 2. Now, when we look at the limit as we approach 3 from the left side, that's when we're on the parabola. And we would expect that value at 3 to be 9. Since these two are not equal to each other, that means our overall limit as x approaches 3 does not exist. How about absolute value? Remember that absolute value can be piecewise defined as x if x is greater than or equal to 0, or the opposite of x if x is negative. When we graph that, we end up with the line y equals x, but only when x is greater than 0, so we don't want this part, and y equals negative x, which is this line. But we only want that part when the x values are less than 0. Right? And that's how we get that distinctive V shape. Now, when we're trying to identify the limit, we want to first look at the limit as we approach 0 from the right of h of x. So coming from the right, when we get closer and closer to the x value of 0, we expect to get a functional value of 0. As for the left side, when we take the limit as x approaches 0 from the left of h of x, that means that we're going to follow the curve from the left side, and we expect to get back at the origin there as well. Since these two are the same, now we can say that the limit as x approaches 0 is going to be 0. I want to take a look at one more special function. K of x is equal to absolute value of x over x. It seems innocent enough, but do you know what the graph of this looks like off the top of your head? Well, let's think about it in terms of that piecewise definition. Because we have absolute value there, the absolute value is x, or the opposite of x. And so k of x is going to be x over x, or negative x over x. Now, that depends on whether x is positive or negative. Notice that this time we don't say or equal to 0 because we can't divide by 0. Can't have 0 in the denominator. So when we simplify these fractions, we end up with only two values, 1 or negative 1. And it'll be 1 if x was positive. It'll be negative 1 if x was negative. When we graph that, for all x values greater than 0, the functional value would be 1. For everything less than 0, the functional value would be negative 1. So let's calculate our one-sided limits. The limit as x approaches 0 from the positive side. So from the positive side, follow the curve back towards x equals 0, and we expect that value to be 1. As for the limit as x approaches 0 from the left, from the negative side, when we follow that, we expect to get negative 1. Since these two are not equal, again, the overall limit does not exist. This is a very fundamental concept, and we'll run into a lot of limits where We just are going to assume that they're continuous and they're nice and there's no big jumps in there. But in order to prove that things are continuous, we're going to need the limit. We're going to need to be able to identify that limit from both sides of the function. And it's something that we should always kind of have in the back of our heads whenever we're dealing with any function.